maybe you need a minute to recover. Mike?
Maybe. Is it? Maybe. Oh, sorry. Just a quick one about detail, Sam. What do you use for dyeing? I think I missed that. Is it just Indian ink or what
Indian
do you use
ink
for sand?
Yeah, black Indian ink if we're dyeing sand. Some of my colleagues have used blue dye quite a lot. I don't like it because when you convert the image to monochrome, you get less intensity out of the blue dye than you do the black. And then you get less contrast between the ambient image intensity from the natural material. So I would always use black. If you need more than one seeding color because you've got layers that you'd like to see in the images clearly, then maybe I'd go to green. But yeah, black generally.
Yeah, I think we've been using blue and green. I'm red-green colorblind, so I just can't go there. But yeah, black. Thank you.
Yeah.
I have a question about the cracks. If the cracks affect the PIV analysis, because when the cracks appear, maybe we have a suddenly low intensity. And also, I have a question about if you have any experience with the stereo PIV.
Yeah, okay. So the first part, yeah, cracks are a problem. And in fact, in NCore and in the new code that we're writing at the moment, we can account for that crack by effectively splitting the subset and bifurcating the problem. You do have to identify where the crack is initially, which is slightly problematic. But yeah, you do want to account for that because if you've got a crack, you've got two regions moving in different directions. And the algorithm is ultimately going to bias to the one that has the greatest signal relative to the other, if it's all encapsulated within one subset. So I think what you want to do is spend time studying your sequence of images in order to work out how to discretize your problem. And then if you get a crack appearing, what I would probably do is I would try and, I would almost run the analysis backwards. I would start from the final state where the cracks are, I would mesh around it, and then I'd run the image sequence backwards, and I'd calculate the strains in reverse. Because the cracks then are coming together. And when they come together, it's less problematic for the algorithm than it is when the cracks are coming apart. So I've done that a number of times.
And, in this case, you updated the frame. You're updating the frame. For example, the reference frame. You have to update it, or you have to use the first.
So I haven't said much about the way that the reference image is updated here. But basically what we're doing is we look at the overall population of measurements and we look at the correlation coefficients. And if the minimum full field correlation coefficient from the whole population falls below a target value that you set and control, then we update the reference image at that point in the sequence. Right? So that's controlled automatically. Sometimes you just want to perform an analysis from one image to the next routinely. And you can do that by setting a very, very low criteria for that image reference frame updating tolerance, right? So you can force the analysis to go sequentially from one image to the next. And there are certain instances where that's useful. But mostly the automatic reference image updating will be sufficient for what you want to do. Your other question that you asked me about stereophotogrammetry, yes, we've used it a little bit. Mainly what we've been using it for is to image the surface of triaxial samples. So we're using multiple cameras, which we know the location of. And so what we do then is we use PIV to find coincident locations in the two output images from each of those cameras. And then we can use epipolar geometry in order to identify the full three-dimensional position of those points on that sample surface. And that's working quite nicely. We're just about to publish a couple of papers with colleagues at UWA on that from work that's been ongoing the last couple of years. In terms of centrifuge model tests, I can envisage that people might want to use multiple cameras to surface the image of a sample. You might want to look at a settlement trough above a tunnel or something like that. We've been playing around with that in Cambridge a little bit, but we've not really seen any meaningful output from that. I think it's quite challenging to identify where the coincident points are in both the camera's field of view. And we've done quite a lot of work where you take a sensor location in one image, you project its position onto your model in order to then infer where that point ought to be in subsequent other camera fields of view. And then you can use PIV to refine the measurement. But I've not seen much output from that yet. That's more Stuart Haig's work than mine. Yeah.
Thank you for your presentation. Very nice. Do you have any experience with analyzing liquefaction problems with PIV, obviously?
Personally, no. As in, I've not personally run any of these analyses. I have had interactions with a number of people, particularly at Cambridge, who were working on liquefaction problems. So Orestes Adamidis was one. There was another couple of students in the last few years working on those problems. In essence, as long as you've got good quality images with the right resolution, the problem is no different. To the PIV algorithm, you've just got arrays of image intensities. So in principle, as long as you've got good quality images, it's the same issue. The challenge is that I think in a dynamic environment where you've got typically more modest camera resolutions in order to get very high frame rates, getting the right image quality is more of a challenge. Mike again?
Just going back to the one about the settlement troughs, is that trying to get the same kind of accuracy as you're getting from PIV, or are they just trying to capture a trough? Because there must be other ways to do it.
Yeah, I mean, the question about the motivation of why to do it with PIV is an interesting one. There are other ways to do it. They're getting spot measurements with LDTs as well. I think the idea of using the PIV is just that they can get more spatial resolution of the measurement points. Effectively, you're sort of semi-unlimited in a sense. You can just choose how closely you want to space your subsets. I think in their case as well, what they were trying to do was they've been modeling a tunnel boring machine as it advances into the soil sample. So instead of doing the old classical plane strain tunnel modeling problems where you just control segments of the volume of the tunnel, they're trying to do it all in flight. And so the whole settlement trough is propagating and evolving in shape. And I think that was the attraction of trying to use, in their case, an array of Raspberry Pi cameras. I don't know why I haven't seen any output from those experiments yet, because the comparable experiments they performed in the drum centrifuge on slope stability problems look really nice. But I'll have to go and have a chat with Ahmed Alaga, a PhD student, and ask him what happened to all the images he took with the settlement trough analyses. And hopefully, if they've got some good results out of that, I shall be able to add that in subsequent versions of this.
I think it's just that they're obviously trying to do it in flight, do something realistic. So
yeah,
obviously
yeah. So it's the propagation with time. Yeah. Question in the middle, yeah.
Yeah. My question about there is some robots in the exploration, the subsea, and their measurement with the imaging. What do you think about it?
You mean taking pictures off an ROV in order to measure displacements, or?
Yeah, but in the subsea exploration.
I suspect what they're doing is surveying. So they're probably taking pictures from multiple viewpoints and then using structure from motion to get the topology of the seabed around whatever object they're looking at. The big challenge that you've got in that sort of an environment is you're not in control of the image texture, right? The seabed is what it is. You can't go and pepper it with modeling flock or dyed black sand. I mean, you could, no one's going to do it. So you're always limited by how much natural texture there is on the seabed, wherever it is you're operating. So if you've got a sandy seabed, maybe there's sufficient texture to get by and to get a nice SFM type analysis out of that. If you were in a murky clay at the bottom of the deep ocean, I suspect it's going to be very difficult. Yeah.
I suppose the images you presented are taken continuously with the camera. What about taking the frames out of a video? Is it the same?
Yeah, I mean, it's the same thing, right? An image is just an array of integer value numbers. So if you can extract them from a video sequence, that's fine. In fact, a lot of the Raspberry Pi based systems that we've been using at Cambridge, we tend to record videos from them at full resolution and extract the frames after the fact. I'm not entirely sure why that is, but it works just fine. So you can absolutely do that. Any other questions? Mike again?
One of the challenges always on strain is keeping the thing against the window. You know, the simplest thing sometimes could be saying, have you got any good research on that stuff?
Yeah, so that half space problem with the jackups, we actually we sort of preloaded it against the window. So we designed it so that if my right arm here is the window and my left arm is the jack up, we would press it against the window at a slight angle so that it sort of ended up bending onto the window. And then it was sort of trying to rotate back into the window to get a good seal. It's alchemy. It's trial and error. They're horrible problems. I mean, if you can do it in plane strain, all the better.
May I add something?
Yeah, go for it.
So now in the visit we will do in the centrifuge, we will also visit the MTG of Liam, and you will see there one way to do this, the way it was applied for a breakwater. So I don't say more, just when you visit there, Liam will show you the model breakwater, and he will explain how this was achieved, which is kind of similar to what you said, but you will actually see it. Okay.
Nothing better than a live example. One thing I will say, and I've not really talked about it here at all, is friction. Everybody ignores the effects of friction. We all just assume the friction effects on the window are modest. They're not. They're horrendous. I mean, we've just spent the last couple of years really trying to measure the effects of friction, and the output's pretty alarming, actually. So my conclusion with all of this, particularly in SAM tests, is PIV is nice in the sense that it gives you the deformation mechanics. I don't think the friction on the window is really influencing those mechanisms much at all, but it's influencing the amount of work done internally in the model quite significantly. And of course, that's a function of the thickness of your model as well. The thicker your model, the less influence the end effects have, but the friction can be significant. Bear that in mind, depending on what you're trying to do with the data. Yeah, question here.
Maybe just one question as an outlook, because you only talked about the plane problems, but there are also some like three-dimensional problems as in the triaxial test. What is the state of the art? Because I think the problem is the sample size and the accuracy. Oh, yeah, you can't measure the whole sample deformation in the same accuracy as you do, for example, in.
So the problem with the 3D measurement is you only get a surface measurement. So if you get the displacements on the periphery of a triaxial sample, but you'd like to know what's happening internally, you have to infer it. We're working closely at the moment with a bunch of people from our information engineering division who are interested in AI and machine learning and a lot of other things with buzzwords I don't understand. But in essence, what they're saying to me is if we've got really nice high spatial resolution measurements across the surface of the sample, they think they can get a pretty good guess at what's happening internally from that across that whole surface. Whether I believe them or not yet, I don't know, but there's potential scope for that. They've also seen a few people playing around with transparent soils and measuring truly internal 3D deformations. I think there's some scope in that, but there's one big problem with those transparent soils, particularly the ones that are mimicking clays, and that is they're very, very light. They've got a very low effective unit weight. So even if you shove them in the centrifuge to try and get the stress similitude right, you've got an additional scaling factor there because the effective unit weight's about a fifth of what you'd like it to be. So ideally, you'd have to run the centrifuge even faster than you would for a real material. And then on the glass side, I've never really seen a transparent soil made of glass that really allows you to have a sufficient size of sample in order to get a meaningful 3D PIV measurement. So, you know, I think there are limitations, and the technique is really best placed for these 2D problems. Of course, the downside, as I've already hinted, is friction. I probably sound a bit pessimistic.
Professor, if you're trying to analyze strain behavior or features on the shear band, is it compulsory to use a micro camera, or you can get meaningful data from a micro camera?
It depends whether you want to see inside the shear band or not. I think if you want to see inside it, then you need your subset needs to be significantly smaller than the size of the shear feature, right? So that's really going to dictate your resolution. And for us, in our case, we're looking a lot at strain localization at the moment, and so we really want a resolution that allows us to put subsets inside the shear band so that the deformation gradient within the shear band is appropriately captured by the subset. So I personally, I think you need multiple scales of resolution in order to do this problem justice.
I have a final one, and is what do you think will be the next step for this type of analysis? What is the next frontier for PIV?
Well, for me personally, I've spent the last few years since I landed in Cambridge trying to take these strain fields and to augment them with constitutive models. So in principle, what I'm trying to do is I'm saying, okay, I'll take a geotechnical model problem where I'm pushing something into the ground. From that displacement and a load that I get a measure of the external work. If I take a strain field and I integrate it with some constitutive model and some assumption of the initial stress state, then I can calculate internal work. The two should be equal. And so I can then optimize the parameters for a given constitutive model to work out what a best fitting set of constitutive model parameters might be. And for me, that sort of quantification is where PIV could go. The big questions I have are whether things like friction are going to muddy the waters too much for me to get meaningful output from those sorts of calculations. So I don't know. Maybe in 10 years' time, we'll all be just saying, this was nice, it looked visually appealing, but ultimately you couldn't really measure that much meaningful stuff from it. Or perhaps we'll overcome some of these problems associated with friction and other aspects and come up with something more quantitative. I think PIV has been a great qualitative tool. It's not been especially quantitative in spite of people calculating strains. They often do nothing with them. They just plot the data and have done nothing with the measurements later on, apart from to say, here's the mechanism. Oh, and it matches my numerical simulation. So I think more quantification is what would come, I think. And with that, I think that's probably the end of the session. So thanks very much for listening.